let's take a closer look at these problems here. We got a spaceship, we got the acceleration, and I want to just review something. This would be a good thing to put on your note card. So if you've got velocity versus time, just so you know, the area under this curve is good for calculating distance and displacement. Now we're going to make a distinction later on in the class, but for now we're going to use those terms interchangeably. Okay. Second thing, if I have a graph of acceleration versus time, okay, if I get this area will actually tell me either the speed, the velocity, or the change in velocity. Okay? So, speed, velocity, or change in velocity. Now, we're going to make a very clear distinction later on with these, but for now, we're just going to label it like this. So speed, velocity, change in velocity. So when we look at these choices, choice B is the clear answer. Now, average velocity and average acceleration. You know what? Again, this is too specific. I don't want to look into this one, so we're going to skip that one. Moving on to the next one. 2 stones drop from the top of a cliff. Stone Y is dropped a short time after stone X. Air resistance is negligible, and we want to know what's going to happen. So this is the way we do this. This is really a tricky one. This is one I might do as a long answer, but just to kind of run through it. The answer is that the distance is going to increase regardless of whether the stone is greater or lesser mass, but let's talk about this. So let's take stone X. Let's see how far it falls after 1 second. So that's S is 1/2 AT squared, where A is going to be 10 meters per second squared. What am I doing here? G is 9.81 meters per second. Whoops. So S is 1/2 AT squared. A is equal to 10 meters per second squared. I need to use IB notation. And that's because really A is equal to G, which is 9.81 meters per second squared. But I'm rounding it to 10 for the sake of this calculation. Now let's see how far it falls after 1 second. So 1/2 times 10 times 1 squared gives me 5 meters fallen after 1 second. Now let's see how far it falls after 2 seconds. After 2 seconds, it's going to end up being 5 times 4, which is 20 meters. Now let's think about this. I drop 1 stone. I drop stone X. Okay, so at 0, so I drop stone X. After 1 second, it's at 5 meters. And after 2 seconds, it's fallen 15 meters more. Now, let's say we drop stone Y 1 second later. If we do that, when this is at 15, this is only at 5 meters. So what we're seeing is that the separation is increasing. And notice mass, weight, none of that has anything to do with it. Now, for number 6, these are graphs that we want to have memorized. So we have air resistance that we need to account for. We want to know which one shows speed versus time. Again, we're going to increase speed, and then our speed's going to level off to a steady value. So which graph reflects that? Graph C. Here, I'm going to skip this because it's just too specific about velocity versus speed. I don't want to do that. Now here, once again, we have an acceleration versus time graph, and we want to know what the velocity is. So we need to use the area, and we want to what the velocity is at 6 seconds. So this is a triangle. I'd want to get the area formula of a triangle in my note card. So I'd have 1/2 times the base, which is 6, times the height, which when I actually count this ends up being 12 when you count the squares properly. And that's going to be 36 meters per second. All right. I think it's a good place to stop. We'll do some more videos, or do more problems in the next video set.